For centuries, we've only had the solar system to tell us how planets form.
We always start with the assumption that we are normal. Turns out that we were entirely wrong.
Now we're discovering thousands of worlds around distant stars, giving us a completely new insight into planet formation.
We're seeing massive planets where they shouldn't be. We're seeing planets forming much faster than we thought was possible.
We're really tearing up the rule book for how to build a planet.
Each discovery writes a new chapter as we work to answer one of the universe's greatest unknowns.
So how do you build a planet? Great question.
Understanding planet formation is asking where we came from. How did Earth get here? These are perhaps the most fundamental, oldest questions in science or even in humanity.
In the Chilean desert, the ALMA Observatory scans the skies. Its mission is to photograph planets forming.
ALMA is a new window on the universe. It's an array of telescopes, of dishes, that look at light that's far outside of what our eye can see.
ALMA takes pictures of young exoplanetary systems when they're still just disks of gas and dust. These disks are planet-building factories known as protoplanetary disks. For the first time, we can see new planets as they roll off the assembly line.
These disks are what we need to observe to answer fundamental questions about the conditions out of which planets form. The previous images, we could barely tell that there was a disk. So you saw a blob.
Now, you basically point ALMA toward these things, and then boom, you've got this gorgeous picture of a disk in far higher resolution than we could have ever dreamed of.
We can actually observe these disks and observe the structure in the disks to watch planet formation happening almost in real time.
One of ALMA's first high-resolution images is of a protoplanetary disk around a star called HL Tauri. The star is less than 1 million years old, but the image reveals evidence of planets already forming.
People saw that there were these rings or gaps in the disk where there didn't look like there was much material or any at all. One of the ideas that immediately appeared was that they might be telling us that there's actually a planet already in that very young planetary disk. So that tells us that planets form fast. Maybe not all of them, but at least some of them had to form really fast.
To understand how HL Tauri's planets form so quickly, we need to look further back in time, to the birth of the star itself. HL Tauri started life as a cloud of dust and gas. But when part of the cloud became cold and dense enough, it started to collapse under its own gravity.
As this gas and dust squeezes together and collapses, it starts to spin faster.
The analogy you always give your freshman physics class is a figure skater pulls in their arms and they spin faster as they pull in.
As the young star spun faster, the material around it spread out and flattened to form a protoplanetary disk, a planet-building factory.
So a protoplanetary disk is made out of gas, hydrogen, helium, some other trace amounts of heavy elements in gaseous form, but also solids, dust, and initially these are really tiny little grains, comparable to the tiniest smog dust that you might breathe in without even realizing it.
How can such tiny grains build something the size of a planet?
Our conventional idea of how that planet building process started out is that maybe something like electrostatic forces help the dust grains clump together into, little inch-size sort of clusters.
Oh, perfect, beautiful, oh my God.
To test this theory, Dan Derda experiments in zero gravity, not in space, but on a plane in free fall.
Where we can carry dust grains in a little plastic box and shake them around and actually literally watch them clump together by these electrostatic forces.
When dust particles rub together, they generate an electrostatic charge. This charge attracts or repels other particles.
It's not so different from how dust clings together under your sofa to form dust bunnies and things like that.
So the dust can stick and grow, and eventually your dust can become centimeter-sized pebbles.
But there's a problem. Once the dust sticks together into pebbles, the pebbles stop growing.
When you get a small pebble, maybe half an inch or so in size, their electrostatic forces are less powerful relative to their size, and so they're not able to stick to each other. They bounce off of each other.
The pebbles reach the bouncing barrier.
So there's a limit, there's a barrier to how far or how large dust can grow. That dust will grow to a size whereby instead of coming together at low speed and sticking, they're going to come together and bounce off of each other, and that's your bouncing barrier.
Imagine the pebbles in the protoplanetary disk are skaters going around a track.
They're flying around at high speeds, and they're solid objects, so when they slam into each other, they're just going to bounce off of each other and ricochet around the ring, and there's not going to be any coherent clump of them that starts forming.
The bouncing barrier is a huge problem. If you can't grow past a millimeter or centimeter, you're never going to form your planets. It's the whole game. We have to take the next step.
Electrostatic forces are too weak to help pebbles take the next step and grow beyond the bouncing barrier. Other forces must be bringing the pebbles together.
So these really small things are moving through the disk, and they're being strongly affected by the gas of the disk that slows down their orbits and changes their speeds and so on. And it actually causes them to drift towards the center of the disk, the midplane, where they all sort of collect. If you get a bunch of them in the same place at the same time, they can kind of shield each other from the interaction with the gas. It's kind of like cyclers in a peloton, all lined up to block the wind from their front.
As the pebbles orbit the star, gas in the disk slows the pebbles down. A wake forms behind the first pebbles, and others line up behind. A group of pebbles sheltering from the headwind.
And this group can form a dense clump. And if the clump is dense enough, gravity can take over and contract that clump into a new planetesimal.
So the way to conquer the bouncing barrier is to form one big planetesimal in one big step.
Planetesimals are important planetary seeds. They can be up to hundreds of miles wide.
They are going to grow up someday to be fully fledged planets.
But how planetesimals grow into fully fledged planets has been a mystery. Until now.
Could a solution be lurking in the outer regions of our solar system?
NASA's New Horizons mission may have the answer. In 2019, NASA's New Horizons spacecraft journeyed through the Kuiper Belt, a dark patch of space at the edge of the solar system. The Kuiper Belt is filled with chunks of rock and ice, relics from the formation of the solar system. New Horizons' mission to help us understand how planets form by taking the first ever photos of an ancient and mysterious rock called Arrokoth, or to scientists, MU69.
So New Horizons flew by this very distant, cold Kuiper Belt object in January 2019. And the reason that that was important was because what we're looking at is truly the first primordial remnant of solar system formation that we've ever seen. This was the first time we'd ever really seen a building block of a planet.
This grainy image shows a weird 22-mile-long rock. It looks like a pair of planetesimals stuck together with glue. The photo reveals a missing stage of planet formation.
What this is telling us is that you don't always just get two objects smashing into each other. They can actually very gently coalesce. And this tells us a lot about how smaller objects aggregate to form bigger ones.
MU69 formed 4.5 billion years ago when the gravity of two planetesimals pulled them together.
Two separate bodies were orbiting each other and ended up getting kind of pushed together at really low velocity and just stuck the head right on the shoulders.
And there's also friction that as they brushed against each other, the ice that they're made from, that energy would have melted them and then refroze. And so it's that combination of sort of a slow coming together, the gravity wanting to hold them together, and then the ice kind of creating that bond that was enabling them to stick together.
Bonded together by gravity and friction, the two planetesimals became MU69, a planet-building fossil.
MU69 is almost like the missing link. It's showing us what happened right after we went from dust and pebbles to planetesimals.
MU69 shows scientists how planetesimals, or groups of skaters, combine and grow.
The skaters that you want to grab to build a bigger planet are whizzing by that planet at high speeds.
The skaters reach out to catch other skaters, like a planetesimal's gravity reaches out to grab other planetesimals.
Eventually, planetesimals will find planetesimals and they'll hit at speeds that allow them to combine and to grow and go off skating together.
The inner region of a protoplanetary disk is a chaotic and violent place. Collisions between planetesimals are frequent. "20-mile-wide planetesimals fuse together and go on to form 1,000-mile-wide protoplanets.
As the bigger you are, the easier it is for you to grab gravitationally other objects like you around you in the neighborhood and grow even bigger.
When protoplanets form from dust, pebbles, and finally planetesimals, it's known as the core accretion model of planet building. We think this is how all planets are born. But looking around the solar system, we can see that while all planets are born equal, they grow up very differently. Why are the planets in the outer solar system huge? And planets closer to the sun small? Could it be because of what they ate as infants?
It really is to do with the chemistry and the physics of the solar system that gives you these very different sizes of planets in different regions.
4.5 billion years ago, the sun plays a big role in the chemistry of the infant solar system. Near the sun, temperatures are high.
it's too hot. The gas is too energetic and it escapes and you lose all that gas. So what you end up with is mainly rock and metal in the inner solar system because that's what's able to survive the early heat of the sun.
The rock and metal that survives eventually forms the terrestrial planets, Mercury, Venus, Earth, and Mars. Further from the sun, it's cooler. Around 250 million miles out, it gets so cold that we hit the frost line.
So a frost line is the point or distance from a star where you get far enough away from the star that it's so cold that water freezes and becomes solid ice as compared to gas or vapor.
Beyond this frost line, there suddenly becomes a lot more material to make planetesimals from, where there's a lot more water available, primarily in its frozen form, in the outer solar system than there is, rocky mineral and metallic matter in the inner solar system.
Beyond the frost line, the presence of water ice helps double the amount of solid planet-forming material. And these icy building blocks can bond together very easily.
With water in the equation, you now have this frosty Velcro-like surface on the planetesimals, and it's that extra stickiness, that extra gripability that can help accelerate the accretion process.
So we can build bigger planets beyond the frost line because there's more solid material to work with because stuff like water has turned into solids, and because that solid material is more sticky.
This extra sticky material helps build colossal planetary cores. Planets, like Jupiter, become gas giants.
To form a gas giant, it's simply about having a large enough core to have enough gravity to start grabbing gas and holding on to it. And that's it.
Once you've accreted a protoplanetary core that's maybe 10 or 20 Earth masses in size, you can now very rapidly start to grow much larger by drawing in the gas.
All of a sudden, things are falling in an almost uncontrolled way, a runaway gas accretion. And that's how you build a giant planet.
Core accretion should explain how all planets form. But when scientists try and apply the model to Jupiter, it doesn't work.
So if you try to build Jupiter's core, you run into a timing problem. So the time it takes to build a core big enough to form Jupiter, that might take 10 or 20 or 100 million years.
And it turns out that's too long.
As Jupiter is forming and starting to accrete all that wonderful hydrogen and helium, the sun is getting warmer and pushing all that material out of the solar system altogether. So as Jupiter's growing and feeding, it's like, hey, what are you doing to all my food?
The growing gas giant is in a race against time. The planet must fully form before its food runs out. Building a planet is no easy feat, with many tricky steps along the way.
Each one of these steps, going from dust grain to pebbles to planetesimals, takes a certain amount of time.
If Jupiter had to wait for distant rocks to collide and fuse, it would take 100 million years to form. And that's not possible, because our young sun attacks the gas in the protoplanetary disk.
A gas disk around a star can't last forever. The star is igniting and becoming active.
The clock is ticking. There's a young star in the middle, and young stars give off violent bursts of radiation, all kinds of solar storms, blowing away the cloud. So if you're going to be a giant planet, you have to move fast.
We know our protoplanetary disk only survived for about 4 or 5 million years. So we know that Jupiter was finished forming only 5 million years into solar system history. And that means we have to really jumpstart that process and get Jupiter to build a really big rocky core really, really fast.
Jupiter needs a giant core of rock and ice so it can grab nearby gas in the protoplanetary disk. The planet must rapidly build its core and capture this gas before it's blown away. To find out how Jupiter's formation was turbocharged, scientists turn to the Very Large Array in New Mexico.
Modern telescopes are really changing the game in how we study planet formation. They can observe protoplanetary disks in ways never possible before.
The Very Large Array peers 176 light years across the galaxy to a young star called TW Hydrae. The goal is to investigate the protoplanetary disk around the star using different wavelengths.
The observations that we have at different wavelengths can tell us what the disk is made out of to some extent. So when you look at an object in radio waves, you don't see the individual object, but you can observe their collective effect on the radio waves.
An individual pebble is too small for the array to see. But the wavelengths of the radio waves picked up from TW Hydrae reveal that small, pebble-like objects make up the disk. But how can pebbles speed up planet building? To work out how Jupiter forms faster, we must wind back the clock to the earliest stages of planet formation.
So in our protoplanetary disk, we formed our first planetesimals, and we formed these out of all of the little pebbles that are out there in the disk. Now what? Still around its neighborhood and everywhere throughout the disk are a huge number of those smaller pebbles.
When we add these leftover pebbles to planet formation models, things go a lot faster.
Adding these pebbles to the mix, adding this to the models, was the big key.
These little pebbles can actually supply a lot of mass to these growing protoplanets. That's pebble accretion, and this is a method of actually accelerating the growth of early protoplanetary cores.
Now when a planetesimal forms, it no longer needs another planetesimal to grow. It can feed on the surrounding pebbles.
So this planetesimal has some significant gravity. It can start grabbing nearby pebbles and growing by accreting them. And this planetesimal has a huge reach because of how slowly these pebbles are drifting by. So it can reach way out and grab a huge number of pebbles really fast, and that'll enhance its growth rate. And this first planetesimal can grow really, really fast, eating up all the pebbles around it.
It's a feeding frenzy. By gorging themselves on pebbles, planets can grow around 1,000 times faster than with planetesimals alone. But when we use pebbles to model the formation of the solar system, something strange happens.
Pebble accretion, when we model it, it can be so efficient and so fast that if you just start with a disk full of pebbles and they start making planetesimals, each planetesimal could grow to be something like the size of the Earth, really, really fast.
Instead of forming giant planets like Jupiter, you'd form 100 smaller planets like the Earth, and this is clearly not what we're seeing. So there must be something else going on.
To understand how the solar system formed, we need to look at how the growing planets interact with each other.
So your first object in your disk that starts growing by pebble accretion is going to grow really, really fast. But the next object is trying to form from the same disk, the same pebbles, but it's growing nearby the first one.
As the infant worlds grow, their gravitational pull increases. Larger protoplanets bully their smaller neighbors.
This really big neighbor can perturb its orbit, can shake it up and down, and by lifting them up and out of the disk, they can essentially starve them, keep them from accessing all of those pebbles to grow.
Pushed out of the material-rich disk, the smaller protoplanet starves. The larger protoplanet thrives, gorging itself on pebbles. Pebbles help explain how outer planets beat the clock and grow large before the sun blows the protoplanetary disk away. By growing from pebbles, Jupiter and the other giant planets grew in just a few million years.
When we insert pebbles in our numerical models, our theoretical models, we can suddenly make these growth processes happen on those observed timescales.
Pebbles help Jupiter grow into the solar system's largest planet.
It can form the core big enough that it would very rapidly start to gobble up the gas around it and become the Jupiter that we see today.
The gas around an infant planet not only feeds its growth, it can push it through the infant solar system, which is not good news. Because giant planets on the move spell disaster for other growing planets. July 2019, we discover 4 strange planets. WASP 178b, 184b, 185b, and 192b. All 4 planets are gas giants. They're strange because they orbit their host stars at least 4 times closer than Mercury orbits our sun.
The physics on this is very clear. You can't form a planet that close to its star. You just can't get the gravity to attract enough material to do that. The star disrupts it.
Stellar winds, radiation, and the immense gravitational pull of a star should prevent any planet from forming where the WASP planets orbit. But looking around the Milky Way, there are hundreds more giant planets orbiting just as close to their stars.
It happens so often that it really took us back to the drawing board to understand what could actually drive that process.
Planets can't form so close to their stars, so we think they grow elsewhere and wander inwards.
This planetary wandering happens during the earliest stages in planetary formation, when that disk of gas and dust from which the planets formed is still there.
These gas disks outweigh all of the planets combined. There's thousands and thousands of Earth masses of gas. And those gases interact and push and pull on the planets with significant force.
As the planets grow, they clear a gap in the disk, and you create sort of an inner disk in the gap where the planet is and an outer disk.
So if a planet cuts a gap and the gas can't get through, all of that gas piles up behind it and just pushes. So you have thousands of times more mass than your planet pushing on your planet. It's like putting something in a flood. It's just going to overwhelm it and push it downstream. And the planets are just getting pushed downstream towards their star.
Could a migrating planet be responsible for one of the greatest mysteries of the solar system?
When we look at the masses, the sizes of the planets in our system, there's kind of a pattern to it where we have, a relatively large Venus and Earth, and you've got massive, mighty Jupiter and Saturn out there. In between, there's Mars, where there should have been enough material to make a much larger planet, much larger than puny little Mars is today. And so that raises kind of a question, why is Mars so small?
Mars is, curiously, a factor of 10 less massive than the Earth. It's not particularly easy to explain with any standard model of planet formation. In fact, it looks like something took a big chunk of mass right out of the middle of our solar system.
That something could have been Jupiter. A few million years after the birth of the solar system, gas in the protoplanetary disk pushed the newly formed gas giant in towards the sun. Jupiter barged through the disk, flinging planetesimals away from the region where Mars will form.
It essentially scatters everything in its path. It's the biggest player, it's the biggest planet. So Jupiter drove away a bunch of material that Mars wanted. It essentially stole its lunch and left it to starve.
If Jupiter hadn't wandered, we might have a mega Mars, 10 times as massive as it is today. But the Jovian giant wasn't the only planet on the move.
At the same time this is all happening, Saturn's migrating inward as well.
The two gas giants became gravitationally locked, their two fates intertwined.
At some point, they got into a configuration where Saturn basically hit the brakes, yanked back on Jupiter and said, yeah, that's as far in as you get, and then started pulling Jupiter out again.
After a 100,000-year journey, Jupiter left the inner solar system, allowing the rest of the rocky terrestrial planets to form, leaving Mars a fraction of its potential size. Mars is not the only planet to be shaped by Jupiter's journey.
Earth is wetter than it should be from where it formed, so we think there was a contribution from the far parts of the solar system.
When the Earth formed, much of the solar system's free water was millions of miles away.
So a big question is, how do we get water-rich material from beyond the snow line, from the outer solar system, into the inner solar system and onto Earth?
When Jupiter migrated, it passed through a region of the protoplanetary disk full of icy material.
And it scatters a bunch of that material inwards that can eventually find the Earth and can accrete onto the Earth as it's forming and account for all the water that we find on Earth today.
Jupiter's journey showered the growing Earth with water, forever changing our planet. Migrating planets weren't the only things to unleash havoc in the infant solar system. Collisions between protoplanets were common, with catastrophic results.
In the early solar system, it was an extremely violent and chaotic scene.
The young solar system isn't violent collisions and then planets. Oh no, it's violent collisions, planets, and then some more violent collisions.
We're talking about planet-sized things that were colliding with each other and then totally annihilating each other.
February 2019, we find a planetary system unlike any we've seen before. Kepler-107 is 1,700 light-years from Earth. Two of its rocky worlds offer unique insight into planet formation.
They have very similar orbits and very similar sizes, which we would totally expect to have very, very similar compositions and densities. I mean, they're made exactly the same, but they're not. They have almost completely different densities.
The rocky worlds of the solar system all look very different, but they're made up of the same basic stuff with similar densities. The planets in the Kepler-107 system are radically different from each other. Kepler-107c is more than twice as dense as its neighbor 107b.
The only place you get densities that high are actually in the metallic core of a planet.
How do you get this scenario? The only thing we can think of is from a massive collision that changed the character of at least one of those planets.
Billions of years ago, the Kepler-107 system was a battleground. There were chaotic and explosive planetary collisions. A young Kepler-107c was on the front line.
So the idea is that Kepler-107c must have been a larger planet once that was involved in a huge collision. And this collision blew away all of the lighter rock, all of the outer layers of the planet. So what you're really left with is one big core, twice the density of Earth.
Kepler-107c is our first evidence that catastrophic collisions affect young exoplanets. In our own cosmic neighborhood, the fallout from ancient protoplanetary impacts still rains down on our planet today.
There is actually evidence of protoplanets' existence found in the meteorite record. It doesn't look like very much, but inside this meteorite, we find diamonds. In order to make diamonds, you actually need a lot of pressure. So the diamonds that formed in this meteorite must have formed in this really deep part of a large planetary body. But as you can see, I'm holding this in my hand, which means that planetary body must have been completely obliterated. It's pretty upsetting to imagine a planet being destroyed. That being said, I'm very grateful for the sacrifices that these protoplanets have made for us, because now we can really understand planet formation in a much better way.
Diamond meteorites are the remains of a protoplanet destroyed billions of years ago. The Earth didn't go unscathed. 4.5 billion years ago, our young planet started to resemble the world we know today. It had a solid surface, water, perhaps even an early atmosphere, but the infant Earth was in danger.
The last stage of growing rocky planets is called the giant impact stage. By this time, the gas in the disk has dispersed. So there are many protoplanets and smaller bodies orbiting the sun, and they collide with one another to grow into the final planets.
New research suggests one collision may have destroyed the early Earth and created something completely new to science.
So we started looking into the physics of giant impacts. And what we discovered was that giant impacts could make a completely new type of astronomical object, a huge vaporized cloud that extends great distances from the center.
This object is a synestia.
When two bodies collide, that shock wave deposits enough energy to melt and partially vaporize both bodies.
So what we actually think might have happened is the impactor came in and devastated the Earth, devastated the impactor. And you end up with this swirling mass that's now really a mixture of those two things.
This synestia is basically a rotating, gaseously extended, vaporized early Earth. 2,000-degree rock vapor. This is what you're talking about.
For around 100 years, the debris from the collision remains as a cloud of spinning, vaporized rock. Slowly, over time, the Earth and the Moon start to form from the molten magma droplets inside the swirling cloud.
As the synestia keeps cooling, it will shrink in size. And eventually, the size of the synestia will be the same as the lunar orbit, and you'll see the moon begin to peek out.
The synestia keeps shrinking, and the newly formed moon emerges from the molten cloud.
The synestia has a long way to go to make the Earth. All of the rock vapor needs to rain out, leave behind an atmosphere of steam, nitrogen, and then the water needs to rain out to form the first oceans. And then finally, we have a planet that looks like Earth.
Synestias are a radical new theory of planet formation. They may explain some of Earth's early history, and perhaps the other rocky worlds as well.
Venus could also have been a synestia during its growth. In the inner solar system, it's possible that all the rocky planets experienced a giant impact that turned it into a synestia.
Synestias may shift our understanding of how rocky worlds form. And collisions still shape our planet today.
Planet formation never really ends. Material still falls to Earth from space every day.
The Earth is still accreting material from the planetary neighborhood around it. We're still, collecting tons and tons of meteorites every year. So the process has slowed, but in some ways it's still occurring.
It's estimated that 40,000 tons of meteorites and space dust hit Earth every year. But that isn't the whole story.
The Earth is simultaneously gaining matter and losing matter. Our atmosphere is being boiled off to form the ionosphere and the thermosphere. So the question is it a net growth or a net loss?
Earth's mass is dropping. There's a net loss of around 50,000 tons each year. The continual evolution of our planet building never stops. Every discovery of new planetary systems and exoplanets forces us to question our most basic planet-building theories.
As far as we know, planets form around stars, and the planets grow as little clumps of goo, and then they attract other stuff and form planets that we see now. But that may not be the only way to form a planet. It's possible, maybe, to form a planet without a star.
We've discovered thousands of exoplanets right across the galaxy. They give us insight into how planets in the solar system form. But in August 2017, a strange object 3,000 light years from Earth hints at a whole new type of planet building.
There was what looked like a very, very dim star, but it turned out to be too small, not enough mass. It wasn't a star at all. It was basically a giant planet several times the mass of Jupiter.
And it's got the unlikely name of Ogle 2017 BLG 1522L. It's a catalog name.
This thing is what we call a brown dwarf or a failed star, but more importantly, it's drifting alone in the galaxy and doesn't appear to be orbiting any other object.
We thought that planets must form in the planet-building factory of a protoplanetary disk. But planet-like brown dwarfs, like Ogle, drift alone in space, far from any stars. So perhaps it formed another way.
They may form like stars, and that is you have a gas cloud that fragments and a clump collapses, and the brown dwarf forms directly from that.
Ogle formed when a collapsing cloud of gas and dust, just 5% of the mass of our sun, failed to ignite and become a star.
It's something bigger than Jupiter, but significantly smaller than the sun by a large margin, and therefore wasn't massive enough to have gravity crush things down in its nucleus dense enough and hot enough that it ignited nuclear fusion to light up the way a star does.
Without hydrogen fusion in their core, brown dwarfs like Ogle are colder and dimmer than a star, making them difficult to spot. There could be up to 100 billion brown dwarfs drifting through our galaxy. And some of them might not be completely alone.
This is really strange. We kind of think of planets orbiting stars, but there's not really any reason to think that planets can't form around brown dwarfs. This thing may still have a disk of material around it, just like a star would. A planet can form in it, just like a planet would. I mean, why not?
To test the idea, we watched brown dwarf Ogle as it passed in front of a distant star. By measuring the amount of light the brown dwarf blocked out, we realized Ogle had company.
This giant planet had another planet orbiting around it. It was a tiny little solar system where instead of a star in the middle, you have a brown dwarf. So technically speaking, you don't need a star to get a planet.
This strange world orbiting a brown dwarf forces us once again to think about planet formation in a radically different way. As we develop new theories and build new telescopes, the way we think planets form continues to evolve.
Historically, the fields of understanding stars and star formation and understanding planets and planet formation in astronomy have just been separate fields. You worked on stars or you worked on planets. But we're realizing now that that's a new frontier to try and understand how they interact in these very early stages where really both are forming.
That's the beauty of all these discoveries. We're living in a revolution right now in planetary studies. All of these planets are causing us to rethink how our own planetary system formed, and in some ways it's also causing us to rethink what do we mean by the word planet.
We've thrown out the rule book on how to build a planet. We've torn it up and we're learning a whole new set of rules. We might even be playing a different game than we thought we were playing in the first place.